summary here, maybe just talk to you about the parts quick. IL-26 DC generators.
Everybody see that okay? So hit the lights. You guys falling asleep with me. Okay, so we started two classes ago talking about DC generators. I just want to hit a few of the high points, talk to you about the pieces. So we have stator, which is going to be, we're going to call it the frame. Stator is an AC term. Okay, that's okay for us to know about. We have the pole. Yeah, I'm going to hit the lights for this. Have the pole right here. Remember that? See that on the generator? Then we have the field winding around each one of these guys. In between the field windings, what's there? Interpole. Yep, interpole. We have the armature core right here. Armature windings right here. Going to be in a loop. Then, of course, we have this, the commutator, the brush, and then the shaft, of course. Okay? What is the definition of a generator again? Yep. That it is. That it is. What does it use to do that? What electrical principle? Yep. What's the difference between an AC generator and a DC generator? Stop answering, Mike and Mike. Yeah. Let's spread it around a little bit, okay? You two know-it-alls. Okay. Okay, so the summary. Generators convert mechanical energy into electrical energy and operate on magnetic induction. Rotating armatures produce an AC. The commutator changes AC armature current to DC current. Neutral plane is the position where there is no induced voltage in the armature, so right there between the north and the south when we looked at the unit there. The armature is the unit of wire loops with the iron core and the commutator. The rotating part in a DC generator is the armature. Series generators increase their output voltage as load is added. Shunt generators decrease. Series and parallel. Remember what shunt means? Who was having trouble with shunt last week? Who was having trouble with shunt? Maybe it was Corey. Armature reaction. Compound generators contain both series and shunt fieldings. Compound, remember they have both. Armature reaction is the twisting and bending of the main magnetic field, and the interpoles are the small pieces, pole pieces, connected between the main field poles to help correct armature reaction. Wrong way. Not going to worry about setting a neutral plane. Supplying current to a load with a generator produces counter torque, making the armature harder to turn. Okay. All righty then. Get rid of this and let's start talking about. So essentially, a DC motor is everything that a DC generator is, except for instead of using mechanical energy to turn into electrical energy, we're going to use electrical energy to turn into mechanical energy. Okay? We're going to energize magnetic field inside the armature and inside the field, and that is what's going to create the rotation. It's going to turn this into mechanical energy. What do you guys think that is? Mike and Mike don't answer. That right there is a set of DC motors that are coupled in series with this big, huge gearing that are used to pull a man lift in and out of the Homestake mine up in Lead. That's pretty neat. My buddy up in Gillette was doing motor work on this, and he got to take a whole bunch of pictures of this thing. But yeah, this big old bull wheel here has a cable that's running up through here, and it goes up along the top of this thing, and then it drops down into the mine to be able to pull the car back out, the man lift. I'm just telling you not to answer. Don't care if you know or you don't know. Okay, parts of a DC motor. This should look familiar. Okay, so again, we have the field that's going to be located inside the frame. Field located inside the frame. Here's the side view. We have this, which is called the armature, commutator, shaft, slot and wedge. That's the armature slots. Right here's where the actual armature windings tie into the commutator, right there on that guy. Pretty much it. Pretty much the same dang thing. So objectives. After studying this unit, we should be able to discuss the operation of a DC motor, discuss the different types of DC motor, draw schematic diagrams for the different types of DC motors, connect a DC motor for a particular direction of rotation, discuss counter EMF, describe methods of controlling speed of DC motors. Okay, that's what we're going to do. So let's talk about this real quick. DC motor principles. Oh boy, are we going to have sound? Hold on. Pause. Pause. Okay. Shit. So you guys are going to have to be very quiet. Yep.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment.
Hey, bud. Steve, do you hear that?
In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC.
That's better, huh?
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. Force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation.
That looks like something we've seen.
In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source.
Sometimes it's not.
The field coils can be connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor constructions: a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF. A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and DC power sources. To know more about it, please check the next video. Thank you.
You're welcome.
I think it was a robot. Okay, so that gives us a little bit of a visualization of what we're actually going to talk about. So, moving forward, DC motors operate on a principle of magnetic repulsion and attraction, just like all motors do. They use the same types of armature and field windings as generators, but perform the opposite function. Motors convert electrical energy into mechanical energy. Okay, and connected power causes the armature to turn. Okay, here's the figure of just a regular old DC motor. This is exactly what we made in our lab, right? Besides for two of our guys that weren't here, I think everybody here made one of these. There's our DC motor right there, gentlemen. And then, of course, increasing the number of loops and turns increases the torque. Okay? All right, torque and increasing the number of loops. Torque is pushing or turning force that created by a magnetic field of pole pieces and armature attracting and repelling each other. The amount is determined by the strength of the field. That can also be determined by the amount of voltage applied as well. The amount is not affected by the speed or the cutting action. Increasing the number of loops. Real DC motors use many loops and many turns of wire per loop to provide a strong continuous turning force for the armature. Okay, just to remind us what we're talking about there, that picture. I promise you that you're going to need to know that, so be familiar with it. The commutator. In generators, the commutator exchanges AC produced by a machine, which would be like a motor or water turbine or anything like that, even steam from a coal plant. In DC motors, the commutator acts as a rotary switch, maintaining the correct direction of current flow through the windings. So when we're talking generators, we're talking armature is going to be where we take the power out to whatever we're supplying to, and when we're talking motors, it's where we're going to apply the power to spin something. Okay? Commutator forces direction of current to flow to remain constant, and brushes supply power. The brushes are actually what supplies the power to the system. Okay, shunt motors and counter EMF. Shunt motors. Gunnar, what is a shunt motor again? Say it again. Yes, sir. Very good. Thank you. Shunt motors are constant speed motors connected shunt field and parallel with armature. Yep, right there it says it. And now when we're going to even have counter EMF to talk about on this too. Counter EMF is a voltage induced in an armature when it spins through the magnetic field produced by the pole pieces. Does everybody understand that? So we energize our field. So the field itself has a magnetic field around it. And now we're also energizing the armature. So there's going to be a magnetic field because we essentially turn the armature into an electromagnet and we have a field into an electromagnet. And because of that relation, that's what makes the motor spin. But also because of that relationship, as that magnetic lines of flux are being cut by the two different things, there's going to have some resistance to that, and that resistance is called the counter EMF. It's going to be opposite the polarity of the applied voltage. So that's going to be kind of similar to what we talked about with an eddy current. How it's going to be kind of out there going against what we're trying to do with it. So kind of keep that in mind, is that counter EMF is something that we don't want to have happen. We want it to be all going the way we want. The amount of counter EMF depends on the number of turns in each wire, or number of turns in the armature, the strength of the pole piece, magnetic field, and the speed of the armature. So I got a couple little notes to talk about when we're talking about shunt motors. In electrical terminology, a parallel circuit is often referred to as a shunt. So DC motors in which one armature and field windings are connected in parallel are referred to as DC shunt motors. The variations in construction between series wound and DC motors and DC shunt motors result in some differences in the operation between the two types, but most significantly, the difference lies with their speed characteristics, where a series wound DC motor exhibits a direct inverse relationship between load and speed. So that means the more you put a load on it, the less your speed's going to go. So as load goes up, speed goes down. Okay, that's when we're talking series. A DC shunt motor is able to maintain a constant speed regardless of the load on the motor. So that doesn't care what the load is, it's always going to run the same speed. So here is what that schematic is going to look like. There's many different variations, but this is clearly, we have the field in parallel with our armature. Oh man, I like that feature. We can draw on this too, huh? Cool. Man, I just learned something. Learned something new today. I like it. Okay. In a series wound motor, we're talking about a shunt wound right here, but the field windings are connected in series, so that equals the current going through the armature is also going to equal the current going through the field. Because the armature windings of the field windings of a DC shunt motor are connected in parallel,
the shunt motor is split into two parts. Therefore, the current flowing through the armature and through the field are going to be equal. Remember, in a parallel circuit, current's the same, right? Excuse me, that's the opposite way. Let me read what it actually says here before I start making stuff up. So let's see. Because the armature windings and field windings of a DC shunt motor are connected in parallel, the current in the shunt motor is split into two parts, current through the armature and current through the field windings, and the total current is the sum of the two parts. Okay, so the total current equals the total field current plus the armature current. All right. Shunt motors again. So here I'm actually showing you a picture of the field. Okay. Not showing you a picture of that guy's midsection, I promise. This is actually the construction period of when they're installing. This is on a shovel motor. They're actually installing these guys right here are the field, and these are, what are these again? Interpoles. These are the interpoles, and here we got a really cool view of the, of the pole piece right there, that curvature of the pole piece, and then this, of course, this big pack right here. That's all wire, bundled up, little tiny coils of wire. That's a buttload of wire, right? I've seen these guys wind these field packs, and they got this little device that they just, it's kind of like on a motor itself. It just sits and rotates, and then they just sit back there with their spool of wire and just wind that stuff on there. Pretty crazy. How's that field's rotating up there? They're just like reeling up fishing string on a fishing reel. Pretty cool. Very thin, very thin. Yep. They get a shitload of coils inside of there, man. And that is a continuous coil. That's one wire all the way through that whole pack. Yeah, it's very thin. I wouldn't be able to tell you, oh, it's a 14 or anything like that. But I would guess that it's smaller than a 14. If I had to guess, I'd probably say it's close to a 16, maybe 16 or even 18. But it's pretty thin. So that's I think that's at either 18 or 22, but it's thicker than that. Yep. So the shunt field windings of a DC shunt motor are made of smaller gauge wire, but they have many more turns than a series wound DC motor. The high number of turns allows a strong magnetic field to be generated, but the smaller gauge wire provides a high resistance and limit the current flowing through the shunt coil. Therefore, the starting torque of a DC shunt motor is low, meaning that the shaft load must be small at startup. In a DC shunt motor, torque is proportional to armature current, as it's shown as an equation that I deleted because I didn't want to deal with. In contrast, for a series wound DC motor, torque increases as the square of the armature current. This exponential torque-current relationship allows series wound DC motors to provide a high starting torque, and handle high startup loads. So that's just telling me the difference between the fact that the shunt wound motor doesn't have a great starting torque, but it can maintain any sort of speed. So once we get this thing running full speed, we can almost lock this thing down, put as much load on there as we can, and it's going to try to maintain its speed. Of course, if we get too big of a load on there, we will, lock the armature up, and we won't be able to turn it just because of the huge amount of load on it. That's just locked rotor. But as that's happening, as we're loading, since the speed is trying to maintain itself, the way that a DC motor controls its speed is it has to increase its torque or its current. So as we're loading onto this motor, the speed is going to try to maintain the same, but as the speed has to maintain the same, the torque has to come up to be able to maintain that speed. So the speed is going to lead, and how I always remember that is when we're talking DC motors, voltage equals speed. Okay, so when we're talking, oh geez, I'm lagging this voltage down, now my current has to build up. or torque, current is torque, has to build up and get that baby pumping again. Increase the amount of magnetic flux that is inside of that DC motor to keep it spinning at that same speed. Okay, so here's the book's version of what they're talking about here. Essentially the exact same thing that we just saw, but this is the shunt motor with the shunt field connected in parallel with the armature. And counter EMF limits the flow of current through the armature right here. So it's very similar when we were talking about magnetic induction, right? We were talking about, what was that term? I can't remember what the term was. Yeah, slipped my mind. Okay, I'll think about it. It'll come to me. So this is the use for a DC shunt motor right here. In all of the research I've done, that this is what we're talking here. So when we're talking DC, we're going to need something that has to start without a big load on it. This is a perfect application for that. This is a lathe, and when we're starting a lathe, it's not going to be under load because we're not going to have it. We're not going to have the DC motor plugged up right next to what we're beginning to cut. We're going to move the cutting wheel to the actual rotation of whatever we're trying to cut. So at that point, when we have that constant speed, and you can even vary the speed on this right here, you can vary the speed of that DC motor by increasing or decreasing the amount of voltage that you want to have going across it to determine your cutting. But because of their self-regulating speed capabilities, DC shunt motors are the ideal for applications where precise speed control is required. Keep in mind, however, that they cannot produce a high starting torque, so at the load at startup must be small, which is exactly what we'll have here on this guy. Applications that meet these criteria that are suitable for DC shunt motors include machine tools such as lathes, which that is, grinders, and industrial equipment such as fans and compressors. So there you go. One thing I will say on this is that if you have a choice between a DC motor and an AC motor, when you're talking speed control, a DC motor is going to be easier to be able to be maintained to have a variable speed. But if you're talking something that you just want to start and you want to always have it run at a certain speed and you don't care what the speed is, you just always want it running, AC motor is your way to go. Okay, so this is if you need to have a variable speed, like say for instance on here where we need to slow this up or slow it down depending on what sort of a cutting we were going to do on the material that we were working on. But boy, and the reason why of course that is because when we're talking AC and DC, we can plug an AC motor right into the wall any dang place, and it's always going to run at 60 cycles a second. The DC motor, we can't plug it into the wall because we don't have the right kind of voltage. So we have to add a bunch of different stuff to be able to turn the AC voltage that we have everywhere into DC voltage. So keep that in mind if you're ever in a spot where like, man, Brian said you can control the speed on these really easy. Think about it. Think about what you're doing, okay? Don't just run out and grab a DC motor if you need to run a pump in your well house out at your house. So, okay. Speed regulation. The amount at which speed decreases when load is added is proportional to the resistance of the armature. The lower the resistance equals the better regulation. You need more current to produce more torque, but current is determined by CEMF, counter electromotive force and resistance. If field excitation current is held at constant, the amount of CEMF is proportional to armature speed. Okay. When voltage is applied to a DC shunt motor, the armature draws current sufficient to produce a strong magnetic field, which interacts with the magnetic field produced in the shunt winding. So the armature is going to make a field, and it's going to interact with the field. The magnetic field. Magnetic field. Good stuff. This reaction causes the armature to rotate. The rotating armature produces back EMF, which opposes the armature voltage and reduces the armature current. If the load of the motor is increased, if the load of the motor is increased, the armature rotation slows and back EMF is reduced, since back EMF is proportional to speed. So with less back EMF voltage and constant supply voltage at a constant supply, the voltage net increases. So the increase of the net voltage results in an increase of the armature current. Since current and torque are proportional to armature current and torque, that means that, let me read this again. Since torque is proportional to armature current, torque also increases. All right. So finally, this increased torque allows the motor to increase speed and compensate for the slowdown due to loading. Hence, DC shunt motor is able to self-regulate speed and can be referred to as a constant speed motor. So that's kind of basically saying, in hard terminology for me to read, what I was just telling you, that as we increase the load on that rotor and we lag the voltage down a little bit because we've added load to it, that current, the torque is going to increase at a proportional rate to the amount of load that we put on there, and it's going to bounce back up. And here's a picture of that. Speed kills, man. Speed kills. So here's our motor speed running along here at 700 RPM. We have a huge load over here. Our motor speed is going to drop, but as time goes on, the motor is going to pick back up, and it's going to get back up there to where that set point is. Okay? When load is applied to a DC shunt motor, its speed decreases, but the motor is able to self-regulate and quickly compensate for the lost speed. So a little bit of where I would see this is maybe on a conveyor belt. Okay, like over there in Wyoming, I worked on a lot of coal conveyor belts, and part of what I did was work on these DC shunt motors. When they would start the coal system, they knew that, hey, listen, we can't have this belt loaded and try to start this motor because it's not going to have enough torque to. So part of their procedure when they got done loading coal at the end of the day was they made sure that the entire belt was clear. And then that way, when they started the belt back up in the morning, they could get the belt up to speed, whatever speed they wanted to, and then start loading it down, and that would maintain that speed. So. Okay, speed torque characteristics. When a DC motor is first started, an inrush current can be high because no counter EMF is being produced in the armature. The only limit on current is the wire resistance in the windings. So current flowing through the armature produces the magnetic field, which causes the armature to turn. So you still there? I never told you that when all those days you were gone, Reed was pretty sure you were dead. Yeah, it was during this class. Yeah, he didn't respond, so we assumed that you were. Oh man. Okay, so let's just make a quick drawing right here. So what's going to cause our armature to rotate is the reaction between the current flowing through this inductor and this inductor. So we're going to energize this as the field, this is the armature. So we're going to pass current flow through here, and then it's going to react differently across that. And that reaction, that opposition to that current flow is what's going to cause it to spin. Okay, and this is the case for sure in the DC motors on the big shovels that I worked on, and it's depending on how the actual field is wound and how it's wired, it should be pretty close to what's set up on most other applications as well, because we need that opposition to current flow to create that rotation. And I guess I've been teaching a lot of motors. I was going to say something, but I don't think I've told you guys that before. Okay. All right. Do we read everything on this one? Counter EMF opposing the applied voltage causes current flow to decrease That's kind of a different language. So speed torque characteristics continued. With no load connected, the armature speeds up until CMF almost equals the applied voltage and motor produces enough torque to overcome its losses. So here we have current squared times resistance loss and armature winding, the windage loss, windage, munching on some windage loss, and brush friction. So that is all of the possible loss that you're going to have whenever that armature starts to pick up. But whenever we add a load, torque cannot support the load at that speed. At the speed the armature is turning, so the armature naturally slows down, and then counter electromotive force drops. More current ramps up and flows to the windings, and the magnetic field increases strength and torque increases. So when current increases, just assume that torque is going to increase. As a result, the armature current rises when a load is added. Okay, I'm going to try. I have a buttload of recordings of shovels where that is just perfect. Because when you think about the big machine going over, it's dropping its bucket down into the dirt from dumping its load in the back of the truck. So it's dropping down. It's got a constant speed, and then when we stick it into the bank, man, we're starting to really need some current to pull that dirt up. So as we're beginning, the operator's got his hand pulled back, asking for full speed. So as that bucket is engaging the bank, those motors are saying, okay, full speed, but the torque is like, oh, geez, I can't give you full speed. I got this huge amount of load on. So that's when you'll see that current just go up to like 3,000 or 4,000 amps. Just skyrocket up in there to try to generate that speed to get that bucket pulled up through the bank and then hold it while it's going out to dump it in the back of the truck. So it's pretty cool stuff. I wish I could have. I don't have the program to be able to show you guys those recordings. Otherwise, we could go through them. And I'm in the process of trying to get the program so we can look at it. Okay, pretty much covers a good part of DC shunt motors. So we're going to move into series DC motors here. I got you for about another 10 minutes. I didn't plan on getting through all of this. Actually, is there any questions on that? Is there any questions on DC shunt motors? I went through it kind of quick. I promised that before we take the test, we're going to spend a day reviewing this and going back through generators just to make sure. We'll spend a day just kind of hitting the high points and making sure everybody's on the same page. Because by the time we get to the test on this, it's going to be 2 or 3 weeks before we've. My concern is that you guys are going to forget about DC generators by the time we get through DC motors. So, if you guys have any questions while we're going through this, please shout them out, okay? So, if there isn't any, I'll just move into DC series. Pretty much the opposite exactly in parallel. We have our power supply down here, positive. I don't like seeing the positive go through A2, but whatever. So positive is going to go through A2, it's going to come out on A1, and then it's going to go into our series winding, which is going to be S2, go through the field, come back out, and go to the negative of our DC power supply. So field windings are thicker diameter and have fewer turns. All right, the field coils of a DC motor are wound with relatively fewer coils as the current flowing through the field. As the current flowing through the field is its armature current and also requires less numbers of turns. So what that's saying is we don't have to have as many turns in here to produce that higher torque because the same dang amount of current that's coming out of here is obviously going to go through here. So in my mind, I think, well, geez, the armature is the part that's actually doing the work, so that's really got to have a lot of current. But when we're talking in parallel, the shunt wound, the armature, or excuse me, the field current doesn't really even have, all it has to be doing is producing a magnetic field. The field in this guy has to also be maintaining the wire size to where once this huge amount of current gets loaded down on this, that this doesn't just blow out. Man, if we had one of them little tiny wires with a couple of wraps on it and we put it in line with the armature current, that thing would explode. That's a huge amount of current that's going through there. I'm thinking big stuff. I'm not thinking this side's here, obviously. But the currents that I'm used to seeing on DC motors are up to 1,000 amps. And that's, you know, the technology of today makes it to where a regular old electrician, I never even saw a DC motor until I went to what? I was in the trade for 6 years before I even saw a DC motor outside of class. So honestly, when you're talking DC motors nowadays, you're talking mining. That's where they are. So there are no DC motors in the bottle plant either. So pretty much the only place that you're around here that you're ever going to see a DC motor is going to be in a mine. So that's kind of the reason why I always think of that, because that's where they're common, is in the mining industry. Okay, back on the track here. The wire is heavier as the diameter is considerably increased to provide a minimum electrical resistance. So when we were talking the parallel, the shunt field wound, we had a higher resistance to be able to increase the amount of torque. Here we want a low resistance because it's already going to have that low torque on it for being in line with the armature. All right, so the wire is heavier, the diameter is bigger to provide minimal electrical resistance to the flow of the full armature current. In spite of the differences, having fewer coils turn around the running of this DC motor remains unaffected, as the current through the field is reasonably high enough to produce a strong field for generating the field required to produce this amount of torque that you want to get. To understand that better, let's look at the voltage equation in a DC motor. Nah, I ain't gonna worry about that. Series motors and series generators, speed characteristics. Series motors connected series field in series with an armature. Speed is controlled by the amount of load. Increase the load and speed decreases, which decreases the CMF and increases the current and torque. So series motor speed characteristics. Series motors have no natural speed limit and should never operate without a load because it's dangerous. What you'll get when you have a series motor in line is it will just run and run and run until it burns out. It'll just go as fast as it can until that current reaches a high enough spot to where it's going to burn that field out. You'll not have a motor anymore. You'll have an open circuit. They may develop extremely high starting torque. Okay, not really much else to say about that. Okay. So speed and torque characteristics of a series DC motor. A series wound motor has a linear relationship existing between the field current and the amount of torque produced. For example, torque is directly proportional to the current over the entire range of the graph. As is in this case, relatively higher current flows through the heavy series field winding with thicker diameter. The electromagnetic torque produced here is much higher than normal. This electromagnetic torque produces motor speed strong enough to lift heavy load, overcoming its initial inertia of rest. And for this particular reason, the motor becomes extremely essential as starter motors for most industrial applications dealing in heavy mechanical load like huge cranes or large metal chunks, etc. Series motors are generally operated for very small duration about only a few seconds, just for the purpose of starting, because if it's run too long, the high series current might burn out the series field coil, thus leaving the motor useless. Yes, sir.
So you have a parallel motor then?
So what we'll see on mine is an entirely different thing. Okay, some of them, they're like conveyor motors. Some of them could have a mixture of both. They could have the series motor to get the loaded belt started, and then they'd shut that off as the other motor kicked in, the shunt wound motor. But most of the time, all of the DC motors, and to be honest with you, the last time that I even worked on a conveyor, we were getting rid of the DC motors and putting AC motors on, because the technology now has got it to where with variable frequency drives, we can produce an AC motor that gives us the exact same starting torque and all of the benefits of having a DC motor, the speed control, all just right there with having an AC motor. And then with an AC motor, you don't have any maintenance. It just runs. There's no brushes that need changed or anything like that. So it's tough to say, but when we're talking shovels, that's a completely different beast, because the field isn't actually connected, electrically connected at all to the armature. They're different. They're a whole different circuit. You'll have an armature winding, and I got a thing in here that we'll talk about when we come back on Monday, when we come back on Friday, that I'll kind of go through and I'll show you what the difference between those two is. And those are extremely specialized. Joy Global P&H actually designed and built their own motors, and we have a manufacturing facility in Milwaukee that builds all of the motors that we need. They have a bunch of ladies just sitting in there wrapping coil brush or wrapping varnish around copper coils. It's really cool. But, yeah, so 3 minutes till. I want to talk to you just a little bit about where we're going to go here. That's enough for today of me talking. So, like I said, when we took a little break there, we're gonna probably try to finish this up when we talk next Friday. So I'll check and see. I didn't look to see before class if everybody's got their review questions in, but that might be a good opportunity for us to start with just the review questions, make sure you guys are all on the same page with that, and then get into it and finish up, because I don't think I'll have enough to make a full class on next Friday. But then Monday, then we probably better start thinking about doing a little review for the test. And I wouldn't be afraid. Let's see, today's Friday. Just having this is getting me all screwed up with having our lab days. Monday's 2 days behind, kind of in the lab to Friday. So I'm kind of just going to make something up so where we don't get 2 labs ahead. I may open up kind of like what we did with 3-phase motors, the calculations. For 3-phase calculations on Friday, I may just say, hey, look, if you guys want to set up for this review, now's the time to do it. And then we'll just take the test Monday during our class. That's maybe what I do. If you guys have any strong objections to that, let me know, and we can maybe do something different. But it's going to be too difficult for me to keep everything straight if we get much further in our lab with the difference between the Monday and Friday group. Yeah. I'd love to be able to time out, but I don't see lost what I'm going to do. So. Okay, guys. So if you don't have your questions done, for review questions done, you have to tell. I think I don't remember when I put the close date in, but I usually put them, if I have them due on Friday, I usually have them the close date for even getting them in as the following Monday. So if you don't have them in, you got till Monday to get them in with some reduced credit. After that, it's too bad, so sad. So, okay, that's all I got. Yes, sir. It's going to be DC motors and DC generators. That's why I want to have that. We'll take that lab time next Friday and just kind of use that as a review of both DC motors and generators. And then we'll set that up. That'll set us up for taking the test Monday. It'll be hopefully a week from Monday. Yep. Hold on a minute. Let me pause this, and then I want to hear what you have to say.